Hey guys, welcome back. In this video, we're going to look at the 2.5 notes talking about limits to infinity. So the first thing we're going to do is take a look at this graph of the rational function, quantity x minus 3 over the quantity x minus 2. And in doing so, we want to identify some things. So the first thing is to identify any asymptotes. When we talk about asymptotes, vertical asymptotes are going to happen when the denominator is 0 and that factor does not repeat in the numerator. So based on that, we're going to have a vertical asymptote at x equals 2. And the horizontal asymptotes are determined by the degree of the numerator and the denominator. And when the degree of the numerator and the denominators are the same, you're going to take the lead coefficient of the numerator over the denominator. So in this case, you have a 1 in front of x to the first powers. So our horizontal asymptotes are going to happen at y equals 1. So those would be the asymptotes for this particular function. Now, if we sketched a quick graph, that's going to help us talk about the limits as x approaches 2, as x approaches infinity, as x approaches negative infinity. So if we draw a quick sketch of that graph, all right, based on what we just found, we found that there is a vertical asymptote at x equals 2. There is a horizontal asymptote at y equals 1. And if we wanted to identify a few other points, I would choose points on either side of the asymptotes, specifically the vertical. So let's do 1. 1 minus 3 is negative 2. 1 minus 2 is negative 1. So negative 2 divided by negative 1 is going to be 2. So we go right 1 up 2. And then just based on what we know of asymptotes, this graph is going to approach the vertical asymptote that way and the horizontal asymptote that way. And if we plugged in positive 3 for x, 3 minus 3 is 0, 3 minus 2 is 1, 0 divided by 1 is 0. So the graph is going to look like this. So as we look at that, from the graph, we should be able to identify some of these limits. For the first limit, it says as x approaches 2, the limit as x approaches 2 of f of x. Well, 2 is where our vertical asymptote is. We are approaching positive infinity from the left, and we are approaching negative infinity from the right, which simply tells me that the limit does not exist because you're approaching different values from each side. Now, the next thing is asking, what is the limit as x approaches infinity of f of x? So as x approaches infinity, our graph is going this way, and we're approaching that horizontal asymptote of 1. And if we look at the other example, the limit as x approaches negative infinity would be to the left, so our graph, again, is approaching that horizontal asymptote of 1. So, as you look at what's happening, when the limit as x approaches infinity and negative infinity, the graph is approaching those horizontal asymptotes. And that's going to be a key idea in these problems. All right, we got a little note here. It says infinity over infinity is called an indeterminate form. You guys are familiar with that from 0 over 0. So an indeterminate form means we can't really determine the value from that form. You can find the limit in this case, you can find the limit by identifying the horizontal asymptote or by dividing each term by x. Many times we're going to take a look at the horizontal asymptotes. All right, the next idea we got here, it says the idea of limits at infinity is based on how quickly functions grow. So there's 3 types of functions we have listed here. We have y equals ln of x, which is a logarithmic function. We then have y equals x to the 34th power, which is a polynomial function, and then y equals e to the x, which is an exponential function. So in terms of growth rates, the slowest growth is the logarithmic function. All right, in the middle are the polynomial functions. And the fastest growing functions here are the exponential. Now, those rates of growth can help us determine limits at infinity, based on if the numerator is growing faster than the denominator or vice versa. And that is something that we're going to take a look at a little bit later on in these notes. All right, so just this idea of the growth rate of these functions, which functions grow slower versus faster, is going to be important for some of these problems. All right, next idea. We've got limits. Limits at infinity occur at the horizontal asymptotes. So we're going to do a quick review of horizontal asymptotes for rational functions. So it talks about if the degree of the numerator and the denominator are the same, which basically if we have some rational function like a x to the n over b x to the n. And again, you could be adding other expressions to those. In that situation, if the degree of the numerator, which is the largest exponent, is the same as the degree of the denominator, again, the largest exponent, then the horizontal asymptote is going to happen at y equals a over b. So the horizontal asymptote is going to be the horizontal line y equals a over b, which a and b are the lead coefficient of the numerator and the denominator. All right, another example talks about, so that's when the degrees are the same. If the degree on the denominator is larger. So let's say instead we have a to the x over n, b to the x over m, and again, you could be adding other expressions. But the degree on the denominator is larger, so m is greater than n, is what we're saying. If that's the case, then the horizontal asymptote happens at y equals 0. And then if the degree on the numerator is larger, so again, if you took the same example, a x to the n over b x to the m, again, adding whatever expressions you want after, where the degree on the numerator is larger, so n is greater than m in this case, the horizontal asymptote, there would be none. All right. Now, in this particular case, just so you guys kind of understand, all of these can be done using the idea of the degree in the numerator and denominator being the same. All right. And I'm just going to kind of quickly show that to you guys really quick. So if we, in the middle example where we said m is greater than n, so if there's a larger degree in the denominator, I can create that larger degree in the numerator by simply going 0 x to the m on top, plus a x to the n over b x to the n. Well, in that case, they both have a degree of m, and your horizontal asymptote is at 0 divided by b. So horizontal asymptote, y equals 0 divided by b, which has a value of 0. So that still gives you that same horizontal asymptote. Whereas if we look at that bottom example, where we talk about the degree of the numerator is larger, all right, that means n is larger than m. So if we wanted to have the same degree, you could have a x to the n on top, and then on the bottom, you would have to add 0 x to the n plus b x to the m dot dot dot. So you can always add 0 where you need it. And then if I'm using that idea of the degrees are the same, so I take the numerator over the denominator, I get y equals a over 0. Well, dividing by 0 is undefined, which means the horizontal asymptote is undefined. Therefore, there is none. All right. So, guys, I'm going to stop the first. Well, let's just talk about this idea real quick here. So, a graph can have at most 2 horizontal asymptotes, one to the right and one to the left. Now, that's an idea that we're going to take a look at a little bit later in the notes here. But that's something to keep in mind. At most, a graph can have 2 horizontal asymptotes. All right, guys, I'm going to end this video and then pick up on the next page.